So I will just start to introduce the first speaker, which is Dr. Roman Shor. Dr. Roman Shor is an associate professor at the University of Calgary. He is director of GeoS and chair of energy simulation of industrial research in geothermal systems. I don't know if that's two separate things, but yeah, you may explain that later on. Yeah. He's currently also serving as a visiting professor at ETH in Zurich, involved in the geothermal energy and geofluids group there. So he came directly from Zurich, I understand. He got his master's and PhD education in petroleum engineering from the University of Texas, Austin. And he also has a master and a bachelor in mathematics and computer science from the University of Pennsylvania. Impressive background, very good. But maybe what is most interesting for us Norwegians, that is that he also serves as a volunteer ski patroller at the Lake Louise ski resort. And he is also a so-called on-snow instructor. Nice title. And what I understand, that is actually an instructor helping to teach new patrollers how to get injured skiers out of the challenging and snowy terrain. Yeah, cool. So, based on this, Roman should be qualified to take your safely down the challenging geothermal slopes today. So, another thing is also that we should have met on the mountains yesterday, because you, after what I said, you told me in the break that you hiked from downtown Bergen via Fløyen over the mountains, or hidden, like we say in Bergen, to Ulriken. And now it's a good hike. I took the short. I took from Vatlandsfjell up to Ulriken and the steps down. So we might have seen each other, yeah, because we just met. So yeah. But anyway, I really look forward to your presentation, and yeah, amongst telling us the difference between oil and gas drilling and geothermal drilling. So, thanks.
Well, thank you for that kind introduction. And this is my second time in Bergen. Last time was also sunny, so I guess I bring summer to Bergen. So you should invite me more frequently. All right. So welcome. With the thunder in the skies. So I'll be introducing a little bit on the challenges and opportunities within drilling, and then why the problem is such a hard problem, unintended, and why it's such a hot topic, further attended, and why we look into this. And then the background picture is around 20 kilometers from the nearest road in Banff National Park, right outside of Calgary. So if you like mountains and cool landscapes, that Calgary is the Norway of Western Canada, minus the fact that the ocean's about 8 hour drive away. So when we think a little bit about geothermal, what do we think about? We think about wells and going underground. What does the public think about? This, right? So a bunch of crazy scientists have built a new geothermal power plant in Springfield. They're excited because they're looking at their sensors and seeing all that heat coming out. But the normal people are looking out and seeing the Vesuvius emerging within Springfield and panicking about this. So part of our job is also, how do we dispel this confusion between what people think geothermal is and what geothermal actually is? So what I'm going to talk about a little bit today is a brief overview of what we're doing in Canada, followed a little bit by this whole concept of drilling for geothermal, why it's a challenge, and then how can we move all the knowledge we have from oil and gas into geothermal, and vice versa, and then how do we do it in such a way that we're not telling the geothermal folks how to do it? Because there are particular challenges within geothermal that oil and gas doesn't have. And then finally, what are the challenges and opportunities? So in Canada, what are we trying to do? My goal is to try and do geothermal anywhere. Alberta is not a geothermal hotspot. Our geothermal temperature gradients are between 25 and 40 degrees C per kilometer. So okay, not great. I want to see geothermal throughout the entire province, which means that we need to develop systems that are cost-effective and easy to put together anywhere. And to do this, we need to look at the systems approach. Drilling, exploration, to drilling, to the production system. And the key aspect as well is that community buy-in. If Iceland has TV shows in which the geothermal drillers are the bad guys, we have problems and we already have a vision problem or a public perception problem. So how do we work around this to get communities to actually say yes? The way we're looking at this is we're looking at everything from heat flow to well designs. My personal favorite is the potato masher design. The drillers in the room, if you can figure out a way to drill that, please let me know. That's kind of a fun one. And everything in between about how you increase the efficiency of your subsurface heat exchanger. And also, if you're doing open loop flow, what are the challenges around that? How do you understand or deal with new seismicity and reduce those risks? How do you understand thermal flows? And then what's your, say, heat recovery and energy use subsurface? Then on top of that, how do you enable these systems? So utility scale, microgrid type scale, how do you empower those local communities? Geothermal is one of the first energy sources where it's built in a community and then directly used by the community. Almost all other energy systems, that energy is exported elsewhere and then you buy it back from some other utility. Geothermal is one of the first ones where you can use it directly. Small scale solar is the other exception. And then how do you educate the communities to de-risk those projects? And then how do you work with remote and indigenous communities as well? A big challenge is how do you fund this type of research? It's providing funding to do this community engagement. You would think it would be easy. Companies don't really care. They want the technical solution, not the community solution. So what we're trying to do is pull out funding specifically for that to start looking at this. Two quick examples of things that we looked at is how do you do technical and economic potential? So how do you start with a typical geothermal temperature gradient map and maybe an understanding of the overall geology? So in this specific case, what we have is, let's see, let's switch to this pointer. So can you start with a typical, let's say, temperature map where this is your geothermal gradient? You have a cold spot, you have hot spots. How do you then connect it now with your estimated depth of your basement? This is important because drilling through sedimentary rock is a little bit easier than drilling through granite. So understanding the depth of your system, the type of systems that you put together, what are your expected drilling costs? How do you collect all this information and then combine it with your end user, so that customer, the end user for the heat, end user for the power, to start coming up with a geothermal favorability map. So I apologize, this is really hard to see, but I promise there are a couple pink dots somewhere here in central Alberta. Again, Alberta is difficult for geothermal if you look at current technologies. What can we do to make drilling cheaper and end use more efficient? And then this whole province lights up like a red map. And that's what we're trying to go for. Another interesting one that we're looking at is what's the potential for geothermal for the University of Calgary campus. So the University of Calgary has set a goal of 2050 being the day they become net zero or zero carbon emitting. We currently have a combined cycle heat and power plant on campus that provides 15 megawatts of power and 60 megawatts peak thermal capacity. Can we replace that with the geothermal system? So one potential option is this funnel design here, which is the Everloop. I know that Everloop is something that's high in people's minds. Think of it as a massive closed loop underground heat exchanger of various form. How many of these do you need to actually build to supply all this heat and power for the campus? The answer is you need about 4 loops. Each loop has 12 legs, drilled down to 7 kilometers, and that will provide 20 megawatts of power and about 80 megawatts of thermal energy. So 7 kilometers deep, that sounds deep, but it's not impossible. The cool thing though is you look at costs. So the current cost for natural gas plus the carbon tax over the next 30 years will be around 500 million Canadian. The expected cost for drilling those Everloops is somewhere between the $200 to $300 million mark. So if you start looking at the system, let's say the lifetime costs, these systems do become, let's say, feasible. The problem is you're paying those 500 million over 30 years versus paying 200 or 300 million today. So how do you now, let's say, get these things financially viable? The other form of system we're looking at right now is that we're just going, let's say, for heat, so heat only. In Alberta, we have this wonderful problem called H2S. We have a huge amount of H2S in our deeper reservoirs. If you drill in, say, the formation of H2S within the city has issues with that, the residents have issues with that. the regulator says that you must be able to evacuate everybody within 7 kilometers of your well if you're drilling through an H2S zone. 7 kilometers is most of the city of Calgary. So how would you evacuate the city of Calgary if you have H2S blowout on campus? That's a bit of a challenge. So let's say we can avoid this. Can we go for a shallower layer where we know there's no H2S and start building a closed loop type system here? So that's what we're currently going through the feasibility study of. Here's our campus. Can we have just a borehole, a closed loop borehole array that acts as a seasonal thermal storage device? So can we pump heat down in the summer, pull that heat out in the winter, drive the campus energy system, and then put high temperature heat pumps into the buildings? This seems feasible. We're going through the engineering design for this, and we're going to figure out how this works. But for this, if you look at this, there's a lot of wells to be drilled. So that right there is where the drilling challenge comes, where you are drilling tens, 20, hundreds of kilometers of well for one of these systems. Garrett Street, which is what Ever's working on in southern Germany, I think is 150 kilometers of well. So that is a huge amount of drilling and a huge amount of potential to optimize as well. And finally, what types of geothermal systems are out there? We've had a couple of talks already this morning. We talked about everything from shallow surface arrays to a little bit more of those deeper arrays down to about 1,000 meters. You can also start looking at, say, deeper systems that can start pulling out heat and power if you are open loop, so flow through reservoir at around, let's say, 100 to 150 degrees C reservoir temperature. If you are closed loop, you have to go to 200 to 250 degrees C reservoir temperature to pull any power out of that system, because of the thermal efficiencies in the closed loop are significantly lower. However, no pumps, no seismicity, and things like that. So there's a lot of, they put pros and cons for each of those. So for all of these, what's common? There's a black line going downward in every single one of the systems. So drilling needs to be addressed, and economics of drilling have to be addressed as well. So when we're drilling, here's an old picture I have. What do? We have some rigs at the surface. Those rigs have a little bit of power. They rotate something, they flow stuff. Those are the things you can control at surface. All this energy goes through a little piece of steel pipe that goes all the way from the rig down to your drill bit. If you're drilling 150 meters, it's a pretty short drill string. If you're drilling 7 kilometers, that's a pretty long drill string. So that's from here to, let's say, to the airport. So when you have a piece of steel that long, it becomes a very interesting dynamic system. And then at the very bottom, you have this little drill bit that is taking all this energy, or whatever energy has made it there, and is making whole with it. So when we look at these systems, what do we have? We know what's happening at the surface. So we know the energy we're putting in, the rotation rates, hook loads, things like that. We want to control what's down at the bottom. And down at the bottom, we might be lucky and have some sensors. So there's going to be sensors that tell you orientation, vibration, rotation rate, etc. But the problem is, how do we get this data up to here? Currently, mud pulse telemetry gives you 1 to maybe 1,000 bits per second at a latency of 1 to 20 seconds. So it will take you approximately 30 seconds to get a 64-bit number to surface. So that is very, very low rate. The current bit rate to Mars is approaching a megabit. So we have faster data rates to Mars now than we have to a couple kilometers underground. So we have to deal with this very low data rate. We can get wire drill pipe, and from what I hear, the Norwegians love wire drill pipe. However, it's pricey, so I can't afford it. So you can get some real-time data, but otherwise you're left with this piece of steel pipe and some stuff going on at the bottom. We need to understand how energy is transferred from the top to the bottom to try and create what, in, let's say, common words now, a digital twin. So a way to estimate what's happening down below in real time, so we can then optimize what's happening in real time. And then why do we want to do this? Is because we want performance drilling. We want to drill as quickly as possible. One way around this is this idea of mechanical specific energy, which is the amount of energy you're putting into the system versus how much, let's say, rock removal you're getting back out. This mechanical specific energy should be approximately the same as the rock strength. You should put as much energy to destroy the rock as the rock is strong. If you're putting in more, that means you're inefficient. If you're putting in less and the rock is still failing, cool. That means the rock is either really weak or something else weird is going on. So both of those are an option. So this is a very simplified view of mechanical specific energy. Your inputs, your RPM, so your rotation rates, your torques, your axial loads, etc. And then you have this bit efficiency times your rock strength. However, the problem with this is we are not accounting for a lot of what else is going on in the system. So if your well is snaky, so it's not vertical, but let's say it's going off on a tangent. We don't have the geostream dynamics in the system. We don't have torque and drag. We don't have hydraulics. We don't have thermal effects. We don't have pressure effects, or let's say variations in that pressure. So how do we account for all of this, all in real time, in order to make this energy input be as small as possible, or vice versa, we want this ROP, so our speed of drilling, to be as fast as possible. So now, I'm working very closely with Ever Technologies on their deep closed loop systems. There's an NDA around that. So they have drilled a couple wells, and they have a couple German wells coming along. I will talk about Utah Forge, which was worked on by people I know at Texas A&M, which is a good analog for what's happening with Ever, and a lot of the performance has been matched by Ever. That is all I'm allowed to say about the Ever projects without you signing an NDA and giving me your life. So from now on, it's just Utah Forge and what was achieved there. So Utah Forge, for those of you who are not aware, is a project in Utah where they are doing deep drilling through granite in order to test out EGS. So EGS, enhanced geothermal systems, drilling through granite and then trying to frack the granite, and then doing open loop flow through that. The nice thing is it is granite, it is hot, and it is deep. So what can we learn from that? So 2 papers, which is all the following figures that come from them. Again, this has been matched or exceeded in certain cases. So, quick history lesson on how drilling at Forge started. So their first well, where they started drilling, so the top of granite is right about here. Sedimentary drilling quite fast, and then a very slow drilling once you got to that granite section. So the first well was drilled at around 2 to 4 meters per hour. Traditional geothermal technology, tricone bits, heavy viscous muds, lots of LCM. You don't want to lose any fluid. You really want to save operation. 2 to 4 meters per hour. That's going to be a long well. What they ended up doing is the first thing they started looking at was, can we look at hydraulics and mud weight? So high viscous mud, it reduces the ease of the cuttings leaving the bottom of the hole, because you have a high pressure holding that rock back down. So by switching to a lower mud weight, you can double your performance easily. The way they actually discovered this was hilarious. They pumped the wrong tank of fluid, and the tank of fluid they pumped was fresh water. So they put a freshwater pill by accident into the well, and their rate of penetration doubled. They could not understand why. Then they went back and looked at the tanks that they connected. They're like, oh, freshwater pill, interesting. Let's try that again. Again, it doubled. So switching to a freshwater mud, and then if you have pressure concerns, you can do managed pressure drilling. That allowed them to increase their performance. That first, let's say, increase. So they then went ahead and drilled the next well. They got up to 5 to 10 meters per hour consistently. Still tricone bit. The next thing that they tried was a PDC bit. So that's the current workhorse of the oil and gas field right now. And then starting to look at energy inputs, so understanding drilling dysfunction, understanding weights on bits, things like that. That allowed them to move to 10 to 30 meters per hour. And then they continued to optimize and start looking at bit designs. They got 30 meters per hour consistently with 300 to 400 meter bit runs. So that right there is a step change now that makes the economics of geothermal viable. 1 to 3 meters per hour for 100 meters, you're drilling a well for 6 months. 30 meters per hour with 300 meter bit runs, you're drilling a well now for a month and a half. So that significantly reduces your costs. So let me go on time. Again, a lot of plots on here about looking at performance, declines, etc. I'm just going to highlight 2 or 3 of these. So the first one is what typically happens when you're drilling through granite. You start drilling, and either you start off, let's say, a very high ROP, very high speed of drilling, and then if you continue to apply constant weight of bits, a constant force to the bit, you have this exponential decline in ROP. So your sharp bit gets dull, and then slowly starts to fall apart. If you instead apply an ROP limiter, so you drill at a certain maximum speed, You slowly increase your weight on bit, and then once you hit your weight on bit limit, then your ROP starts to drop. So what you're trying to do now, if you're looking at this from an optimization point of view, you want to increase this area under the ROP curve, because that is your hole drilled. You want to maximize that. So which of these two ways is the best way? That's still a question. So this is where we start looking at optimization of what do we want to do with our drilling parameters to have our maximum sustained ROP or the maximum ROP that is again sustained for a longer period of time. What's that effective weight on bits? The weight on bits, you have each individual cutter, it pushes the cutter into the rock. So your rock removal is now a function of how much the bit can dig into the rock itself. The more it can dig in, the more rock it removes, at least until the bit stalls. So there's a balance now between enough effort, but not too much effort, and you want the bit to stay sharp. How many of you have ever tried drilling into your granite countertop at home? How long did your drill bit last there? Not very long. So it's a very difficult abrasive rock now. So now what we start thinking about is how do we design these cutters in such a way that they can take huge amounts of abuse from, let's say, drilling into granite, and then last for a long period of time. All right, so I'm going to skip these three and go to bit wear. So how do these drill bits wear over time? So here's a good example of evolution. You start with just a little bit of wear, and then as, let's say, the bit becomes more and more worn, this diamond space that you have starts to fall apart, and then the carbide that's behind it also starts to wear. So you have this slow, say, decline. So if you think back to that curve I showed, this is you slowly increasing weight to maintain ROP. And then this right here is now when the drill bit starts to become irreparably damaged. And the goal is you want to push this drill bit for as long as possible so that you get drill bits that come out with damage to cutters, but not to the actual drill bit body. These things are replaceable. You just pop them out, put new ones in, you go back and hold. If you destroy the actual matrix of the drill bit, that costs you money, because then you went from renting a drill bit to buying a drill bit. So then you now have another optimization problem of how much can you force the drill bit to drill before it completely falls apart. And then if your rock is very interesting, you can have, let's say if you have a lot of heterogeneity, you can have, let's say, hard versus soft rock. That can cause, let's say, fracturing within the bit matrix itself. If you're going from a soft to a hard lamination, you again have a stress contrast about what gets, say, damaged and wear, things like that. All right, I'm going to skip all these. Finally, going to borehole patterning, you want a straight hole. Depending on your operations, you can have non-straight holes. This is a couple of examples again from Forge, where simply based on what they were trying to do, so this was repetitive steering actions, you have a borehole pattern now that exists. The reason why this is important, in sedimentary rock, if you have a borehole pattern, sedimentary rock is soft, your drill string will wear it out. It will just become smooth. Granite is not soft. Granite will stay ledgy. So now imagine, let's say, this borehole and trying to push these casing through. There's now plenty of obstacles for this casing to get stuck on. So you get stuck now with your horrible borehole. So I did my PhD in Texas. So as a Longhorn, what I would say is this is a borehole that an Aggie drilled. So that's Texas A&M or MP school. I don't know what the equivalent here is. Bergen is the NTNU. All right. Then borehole stability, that also becomes a problem. I'm going to skip that one. So what is needed for geothermal energy to succeed? So you need the reservoir. So you need to be able to characterize it, understand what the temperature and flow properties are. You need to have a reservoir management plan. That's the key one because your wells last for 50 years. How do you manage the temperature in your reservoir? Oil and gas wells last for what? A year before payoff? 2 years? You don't really care after that. You extract additional value, but don't really care because you've already gotten your payback out. For geothermal, you need 50 years of operations. You need drilling technologies, so that's both efficiency as ROP, but also bit life. You need your production equipment, so it's a scaling, longevity of equipment. You don't want to be replacing things every year. And then you want better energy conversions. And finally, challenge. So the big challenge for geothermal, imagine you want 1 gigawatt of geothermal power. That is nice because geothermal power is 90% of capacity factor. It'll produce all year. That's the same thing as 3 to 4 gigawatts of solar or wind. because solar and wind are about 30% capacity factor. So you need battery or some other storage to store that energy to give you a base load 1 gigawatt. And it can displace quite a lot of natural gas if you're replacing natural gas. Cool. Those are the pluses. The problem, though, is you need, if you have 100 degrees C delta T, so you produce at 200 degrees C, inject at 100 degrees C, you need 8,000 tons of water in order to produce that 1 gigawatt hour. If you only have a 1 degree delta C, you need almost 1 million tons. So this right here, so 8,000 tons of water is 72,000 barrels per day per hour, or 1.7 million barrels per day of fluid production. That is almost 2 times the North Sea oil production. Not just oil, not total fluids, because there's also a lot of water in the North Sea. And this is just for thermal energy. If you want electricity, you need 3 to 10 times that. So 1 gigawatt of power is equal to 3 to 10 or 6 to 20 times North Sea fluid production. So that right there is the challenge. How do you produce all that fluid and produce it cheaply? And then why do we care about this now? It's high capacity factor, base load, blah, 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 we know this. And then also the big plus is we can pivot everything we know from oil and gas to this field and move on from there. So where's that next gigawatt coming from? I personally think it's that heat. We've already had quite a few conversations about heat already during the seminar, or during this conference, and also that deeper combined, where you're doing heat plus something else. Just geothermal for power has very limited application. You need that additional use for that heat, because the cooling tower is the worst use of heat on the planet. Well, how else can we use that heat? So with that, I want to say thank you, and these are my sponsors over in Calgary. So with that, I'll leave it for questions and proof that we do have Northern Lights in Canada.
Yeah, thank you, Roman. Very interesting. Questions?
Price for kilowatt hours.
Well, if you look at their corporate deck, their ever 1.0 was 35 cents per kilowatt hour, I think. Their Garrett Street, they're targeting like 15 to 25, and then their goal was to get to 10. That's from their corporate deck. That makes assumptions based for cost per meter drilled. Their big cost savings is that they don't complete any of the lights. They're open hole completions.
What temperature is out?
In order to produce power, you're limited by your service cycle. So right now that will be a binary cycle, so 120 degrees C of service. Well, 110 to 120 degrees C of service. That's your cutoff right now. And that's the same for almost any type of geothermal system, because it will run through binary regardless, and that's the current limit. I have had people come up to me and say they can produce power from 70. I'm a little bit skeptical at the moment.
Do you have any references for a closed loop system? I think you will decrease the extraction of energy.
Yes.
Ongoing. So do you have any system up and running?
So Ever has Lights in Alberta right now. It's been running for 4 years. Yeah, 4 years now. It produces a consistent 150 kilowatts of thermal energy off of a 2 kilometer deep 2-leg system. And they claim their thermal model predicts it perfectly right now. So they do have the capability to model the expected temperature decline. Since the thermal, let's say like the thermal funnel around each leg is actually quite small. Because let's say your reservoir is 400 degrees C. Inside each well, you'll be at 200 degrees C. And then that gradient from 200 to 400 will be 5 or 10 meters. So the closed loop systems don't go far into a reservoir. Because once they get to a steady state temperature, now you just have a steady thermal gradient of heat moving in. And that apparently stays for a long period of time. But I'm a driller, not a reservoir engineer. Yes.
What fluid do you use in the turbines to extract electric energy? Water or supercritical CO2? Or?
There's many options. So for ORC turbines, so for any binary cycle, your fluid comes out of the wellbore, goes into a heat exchanger that then heats a secondary working fluid. So for an ORC, it's typically some form of organic fluid that has a boiling point in the 50 to 60 degrees C range. So the idea there is you take a liquid organic fluid in, it flashes steam or into a vapor phase, and the vapor goes into a turbine designed for that fluid. CO2 can be used, even though if you look at the thermodynamic cycle for CO2, it isn't well suited for that binary cycle, or that binary type cycle. You can do CO2 as your working fluid inside the entire system. That is possible. But the problem with that is your materials and the overall efficiency of the system. So CO2 could be used. At the moment, there's a series of organic fluids you can use for the various organic RC cycles.
For the presentation, Roman. Question concerning the drilling. You said maybe around 1 in we drilled. What is the cost per
Something below 5,000. No, so if you look at again the corporate decks, they have very ambitious targets. They are, in order to make the 10 cents per kilowatt hour work, it has to be quite low. What are they currently targeting? I don't know.
You said that the holes are not going to be completed. In the Geretsried area, I guess the wells will be placed within the Malm reservoir.
Yeah.
How is that going to work with the permeability that you encounter 150 kilometers?
Yeah. So what they when you're drilling, you have a filter cake. So that's the layer of, let's say, solid particles that come out of your drilling fluid and create a layer around the borehole. They are effectively doing that with their own, say, formulation, where they leave a filter cake or a what they call a geothermal cement on the outside of the wellbore. So it's going to be rock, a layer of this material, and then as long as you have positive pressure inside the well to above reservoir pressure, you have no ingress of fluid, and that cement is stable. And their Alberta project was into permeable formation as well, and they lose a meter cube over something. So it's a very slow loss of fluid, but they're working with water, so it's inexpensive and sit back down.
Just a follow-up question, because I think it's very interesting, but I mean it's a karstified reservoir, so there could be quite substantial porosities.
So they need to cure any permeable zones during the drilling process. So if there's significant faulting, then they probably have to go through and cement it somehow. It's like cemented, squeeze it, cement it, and then drill through it. But the goal there is to not have cemented casing.
Basically avoid.
Yeah. Yes. So like when you're looking at open loop geothermal, you want permeable formations. For a closed loop, you don't want permeable, but you can also fix the permeable if needed. So I think their biggest selling point is the fact that they don't care about the reservoir; they just need a seal. They need a pipe. But the question then becomes stability of the pipe.
Yeah. Okay, I'm the moderator. I can have the last question. Okay, you talked about weight on bit and interesting. We know all about that, being in the drilling business, also tripping time, tripping in, tripping out, all this, adding cost to the project. What about automation? How would automation improve drilling performance, and what could be the challenges of automation?
Well, so like if you remember back to the whole craze about automation 10, 20 years ago now, with this whole idea of factory drilling. So you place the rig somewhere, and then you drill there for 3 to 5 years, all in those shale formations. How many of those factory drilling operations actually occurred? 0, right? Because the rig will come in, drill a couple, then move on, and then come back and then do infill drilling. So there's very little of you drill the entire pad out at once. Or something that's like Geretsried, you are drilling out the entire pad over the next 4 years, or however many years that they were planning on being there. So that is prime targets for prime potential for automation, because now you will be in the same formation, in the same laterals for the next 3 years. So I think that's a phenomenal potential right now where the first well can be hand drilled, second well can be optimized, third well now can be automated, and after that you just push a button. Because again, the formations are the same, the fluids, everything is the same. So that should be easy. But I think that there is a very interesting potential for that. And all rigs now are mechanized, so they should be automated or have the potential to be automated.
Yeah, and with the AI and all this coming up, and this research that Equinor has done now on sensing the metal the gas there is quite interesting.
And that and also sensor data quality has gone up significantly as well because people are aware of it. So now you have good data that can potentially be used to train algorithms.
Yeah. Okay, thank you.
Thank you.
Very interesting.